Watch this. An egg falls off a table. The shell cracks. Yolk spills across the floor. Nothing unusual. Now watch it in reverse. The yolk gathers itself. The shell reassembles. The egg leaps back onto the table. Your brain immediately knows something is wrong. But here's the strange part. Every single law of physics works perfectly in reverse. Newton's laws, electromagnetism, quantum mechanics, run them backwards, and they still make sense. There is nothing in the fundamental equations of physics that says time must flow forward, and yet, eggs break, coffee cools, people age. The past is different from the future. So if the laws of physics don't care about the direction of time, what does? The answer is a single number, a quantity so fundamental that Einstein called it the only law of physics that will never be overthrown. It's called entropy, and it is the reason time has a direction. Let's start with what makes this so puzzling. Take a pendulum swinging back and forth, film it. Now play the film in reverse. Can you tell which direction is forward? No. The motion looks perfectly natural either way. The same is true for planets orbiting a star, for billiard balls colliding, for electrons jumping between energy levels. At the microscopic level, physics is completely time-symmetric. Every interaction can run backwards. This is called time reversal symmetry, and it's built into the deepest equations we have. If you showed a physicist the equations of motion for a system of particles, they could not tell you which direction time is flowing. But zoom out. Look at the macroscopic world, the world of eggs and coffee cups and living things, and suddenly time has a very clear direction. Things fall apart. They don't fall together. So somewhere between the microscopic and the macroscopic, something breaks the symmetry. Something makes the future different from the past. In 1877, a physicist named Ludwig Boltzmann figured out what that something is. Boltzmann's idea was deceptively simple. He said, forget about forces, forget about energy. Just count. Imagine a box with 30 gas molecules. At one moment, all 30 are crammed into the left corner. That's a very specific arrangement, a very ordered state. Now, let the molecules bounce around freely. After a while, they'll spread throughout the entire box. That's a disordered state. Here's Boltzmann's key insight. There is only one way to arrange 30 molecules all in the left corner. But there are billions of ways to arrange them spread throughout the box. He called these arrangements microstates, and he defined entropy as a measure of how many microstates correspond to what you see. Low entropy means few microstates, few ways to arrange the pieces while keeping the same overall appearance. High entropy means many microstates, countless arrangements that all look the same from the outside. His formula is carved on his tombstone, S equals K log W. Entropy equals Boltzmann's constant times the logarithm of the number of microstates. And here's why this explains the arrow of time. The system doesn't want to become disordered. There's no force pushing it. It's pure statistics. If you shuffle a deck of cards randomly, you won't get them in perfect order. Not because order is forbidden, but because there's only one ordered arrangement out of billions of possible shuffles. The universe isn't moving toward disorder, it's moving toward probability. The numbers here are staggering. Consider something as simple as a glass of water at room temperature. It contains roughly 10 to the 25th molecules. The number of possible microstates, the number of ways those molecules could be arranged, is a number so large that writing it would take more atoms than exist in the observable universe. Now compare that to an ice cube. Same molecules, but locked in a crystal lattice. Far fewer possible arrangements, far lower entropy. When ice melts, it's not because some force wants it to melt. It's because the number of liquid microstates outnumbers the solid microstates by a factor that has more digits than there are particles in the cosmos. This is why entropy increase feels inevitable. It's not a force, it's not a law in the traditional sense, it's the overwhelming weight of probability. Think of it this way. If you released 1,000 coins into the air, could they all land heads? Yes, it's physically possible. But the probability is 1 in 2 to the 1,000th power. You would have to wait longer than the age of the universe to see it happen even once. In 1867, James Clerk Maxwell proposed a thought experiment designed to break the second law. Imagine a box divided in two with a tiny door between the halves. A microscopic demon sits at the door. When a fast molecule approaches from the right, the demon opens the door and lets it through to the left. When a slow molecule approaches from the left, the demon lets it through to the right. Over time, all the fast molecules end up on one side, all the slow ones on the other. One side gets hot, the other gets cold. Entropy decreases. The second law is violated. For over a century, physicists debated whether this was possible. The answer came in 1961 from Rolf Landauer. Landauer showed that the demon must store information about each molecule, fast or slow, left or right. And when the demon's memory fills up, it must erase old information to make room for new observations. That erasure, that destruction of information, generates heat. It increases entropy. The demon doesn't cheat the second law, it just moves the entropy from the gas into its own memory. Information is physical. Erasing a single bit of information costs a minimum of kT N2 joules of energy. There is no free lunch. So, here is the remarkable conclusion of all the fundamental laws of physics: Newton's mechanics, Maxwell's electromagnetism, Einstein's relativity, quantum mechanics. Not a single one distinguishes past from future. They are all perfectly time-symmetric. Entropy is the exception. It is the only quantity in physics that has a preferred direction. It increases, always, in every isolated system, without exception. This is why we remember the past, but not the future. Why causes precede effects, why we age, why stars burn out, why ice melts in warm water. The arrow of time is not built into the laws of motion. It emerges from statistics, from the simple fact that there are overwhelmingly more disordered states than ordered ones. But this raises a profound question. If entropy always increases, if the universe always moves toward higher probability, then the universe must have started in an extraordinarily improbable state, a state of extremely low entropy. Why? How? What made the beginning so special? This is one of the deepest unsolved problems in physics. The universe began 13.8 billion years ago in a state of astonishingly low entropy. Matter was spread almost perfectly uniformly, a hot, dense plasma with almost no structure. That might sound disordered, but gravitationally, it's the most ordered state possible. Clumps, galaxies, stars, black holes. Those represent higher gravitational entropy. Physicists call this assumption the past hypothesis, the idea that the initial conditions of the universe were special, extraordinarily special. Roger Penrose calculated just how special. The probability of the universe starting in such a low entropy state is 1 in 10 to the power of 10 to the 123. a number so absurdly small that it makes every other improbability in physics look commonplace. We don't know why the Big Bang was low entropy. Some physicists, like Carroll, argue that our universe may be a fluctuation in a larger multiverse. Others, like Penrose, propose cyclic cosmologies where entropy resets between cosmic epochs. The past hypothesis is not an explanation, it's a boundary condition. It tells us what happened, but not why. So, what is entropy, really? It's not disorder. That's a simplification. It's not chaos or randomness. Entropy is a count. It counts the number of ways the microscopic world can arrange itself while looking the same to us. It measures our ignorance, the gap between what we can see and what is actually happening at the smallest scales, and the arrow of time. It's not written into the laws of physics. It emerges from the fact that there are vastly, incomprehensibly more ways for things to be later than before. The future isn't determined by force, it's determined by counting. Every moment the universe explores more of its possibility space. Every second it finds new arrangements it hasn't tried before. That exploration, that relentless statistical drift toward the probable, is what we experience as the flow of time. You are not moving through time because something pushes you. You are moving through time because there are more ways to be tomorrow than there are to be yesterday. That is entropy, and that is why time flows.